Hey guys, Dave here, your Prep 101 Eng 319 instructor. And as promised, here are 3 solution videos to 3 questions that I've emailed to you guys. Let's start with question number 1. So let's say you're at a casino and you suspect that the die that they're using is an unfair die. So what you do is, as a dealer is rolling the die 120 times, you tabulate how many times number 1 came up, number 2 came up, and so on and so forth. And you observe these numbers out of the 120 rolls of the die. Now, just by eyeballing the data here, okay, it seems like the die is a little bit unfair, right? If it were to be a fair die, you would expect to see frequencies that are in the neighborhood of 20. But if you look at number 3, there's some departure from 20. 4 in particular departs from 20 by quite a bit. And even 5 and 6, they are less than what you'd expect to observe had this been a fair die. So you decide to perform a chi-squared goodness of fit test. And the null hypothesis, what you want to show in this test is that the die is unfair against the null hypothesis that this is a fair die. Now, if this were to be a fair die, and random variable x captures, the outcome of a roll of the die, random variable x would take values of 1, 2, 3, 4, 5, and 6. And their probabilities associated with px, that I'm going to call p1, you would expect that to be 1 over 6, and so the same thing for 2, 3, 4, 5, and 6. So had this been a fair die, you would expect all of your PIs to be equal to 1 over 6, or that x comes from a uniform distribution. Had x followed a uniform distribution, you would expect, so the expected value of x here would be, you would expect of the 120 rolls, you would expect 20 of those outcomes to be of number 1. Of the 120 rolls, you'd expect 20 of them to be number 2, and the same for all the other ones. So the expected frequencies would be all 20s. Like that. The observed frequencies that I'm going to denote as O1, O2, all the way up to O6 are as such. So the more our observed frequencies depart from the expected frequencies, which were based on the fact that, or which were based on the assumption that the null was true, that it came from a fair die, the bigger the deviances or the departure from the expected frequencies, the more evidence we would have in favor of the alternate hypothesis that these observations came from an unfair die. So like all other techniques that we use, or all other numbers that we've computed in other types of hypothesis testing, we need sort of one measure, one test statistic that will summarize all of that. And that is called the chi-squared test statistic. And its formula is given by this. So as you can see, the numerator contains how much the observed frequencies deviate from the expected frequencies. The bigger these deviances, the more evidence we have in favor of the alternate that these observations came from an unfair die. I'm going to divide those by EI. So computing those for the first sort of column here will be 26 minus 20 squared divided by 20. And I'm going to compute it for the last one. Do the same thing for column number 2, 3, 4, 5. And for the last one, we get a departure of 7 and divide that by 20. And if we compute that, we get 11.8. And that is going to be the test statistic that we're going to use to test the null versus the alternate. Just like in any other type of hypothesis testing, we have to compare that against a critical value. And the critical value comes from the chi-squared distribution. And alpha, we're told to test this at alpha equals to 5%. So the chi-square critical is going to be chi-square such that the right tail area is equal to 5%. And the degrees of freedom here will be equal to the number of categories that you have. Here we have 6 categories minus 1. So we have 5 degrees of freedom. Go look that up on your chi-squared distribution and you're going to see that it's 11.7. Our test statistic of 11.8 lies in the rejection region, giving us evidence against the null in favor of the alternate. So we therefore reject the null hypothesis and conclude that the die, evidence shows that the die is unfair. Now just to add some perspective here, had you observed some extreme values where out of the 120 times you had say 60 ones show up, you had 42 show up, and I don't know, 5 occurrences of numbers 3, 4, 5, and 6, obviously this would suggest heavily in favor of the alternate that the die is unfair. Using these blue numbers here, had you computed a chi-square test statistic, what's going to happen is your chi-square test statistic will be a value that is deep in the rejection region. The deeper a test statistic is in the rejection region, we argue that the more evidence we have in favor of the alternate. Now, conversely, had you observed frequencies that were close to the expected values, say 21, 19, 18, 22, another 19 and 22, 21, these green numbers don't really suggest that the die was unfair. In fact, it supports the null hypothesis that it actually came from a fair die. Had you computed, again, a chi-square test statistic using these green numbers, you would actually get a very small chi-squared test statistic somewhere in this neighborhood. And that's reflected by the numerator of the chi-square test statistic, which captures the difference between the expected values and the observed values of 21 and 20. And the smaller the differences in the numerator, the smaller the chi-square test statistic will be. And that chi-square test statistic, a small value, will be nowhere near the rejection region, further indicating that we have no evidence in favor of the alternate hypothesis that the die is unfair.